Continuing with our series in quantum mechanics, having discussed about the introductory portion, that is the Hilbert space, we will start off this video with Dirac notation, famous notations given by Paul Dirac, and that involves formalisms which are going to be beneficial for us in our discussion of quantum mechanics in the n-dimensional space. Usually, the Hilbert space is an expanded space with a lot of bases, with a lot of dimensions. Dimensions can extend up to infinity, while in case of rather huge numbers, uh, in case of three-dimensional coordinates, we had only the three coordinates which were helping us, and the wave equations that involved only, or that were restricted only to the three-dimensional formalisms. Here we will be expanding it or extending it, and as you will see, the Dirac notations famously provided by Paul Dirac, uh, they are quite handy in explaining or obtaining the values, uh, just like the probabilities and many more uh, operations that are taking place in that space. So let's get started with Dirac notations. Now, as we see, well, this is obviously analogous to the Euclidean vector space, the Hilbert space, that is. Now, the Dirac, while he introduced invaluable notations on quantum mechanics, it allows one to manipulate the formalism of quantum mechanics with ease and clarity. So what he essentially provided us with are the Ket vector spaces, or Ket vectors, which are denoted as this symbol, and then he had the Bra vectors denoted by the other way around, and finally, putting both of them together, we have the Bra-Ket notation, and as you can see, the Bra vector and the Ket vector together give the Bra-Ket notation because they constitute a bracket. Now, that's the simple idea of the nomenclature that we have. That is, the bracket over here that we get is composed of the Bra vector on the left and the Ket vector on the right. So that is why it is known as the bracket put together. Or from the bracket, we have the Bra vector and the Ket vectors. Now, this notation, as we'll be gradually observing while trying a few examples, we have these notations, one of them to be in the Hilbert space, while the other one, the Bra vector, to be in the dual space or dual Hilbert space. So this belongs to the Hilbert space, while this belongs to the dual Hilbert space. I didn't have a fancier symbol for Hilbert space, so I used that. You can use many other symbols that they use for Hilbert space. Now, as in wave mechanics, we are using the function that is psi rt, which is giving us all the information regarding the wave nature. We in quantum mechanics use the general formalism in the form of the Ket vectors, which means that the Ket represents the system completely. And so let me write that it represents the system completely, and also that, which also means that knowing the value of, or knowing about the Ket vector, knowing this Ket psi, it also means that knowing all its amplitudes and all the possible representations. The Kets are independent of any particular representation. Now, there is no reason to single out a particular representation basis, such as the representation in the position space. Now, if we want to know the probability of finding the particle at some position space, we need to work out the formalism within the coordinate representation. The state vector of this particle at any given time t will be given by the spatial wave function, which is given by the spatial wave function that is of the form RT for psi, and that is equal to simply psi RT. And the coordinate representation we are going to have this psi phi or phi psi, that to be equal to, that is the scalar product that we are taking. So this is the form of the scalar product. In the coordinate representation, they simply mean the conjugate of phi RT multiplied to psi RT d cube r, volume space. Now, similarly, if we are considering the three-dimensional momentum of a particle, then the ket will have to be expressed in the momentum space, and in this case the state of the particle will be described by the wave function that is psi p t. P here gives the momentum of the particle, of course. Having known all of this, let's get into the properties of these kets, bras, and the Bra-Kets altogether. The first things first, every ket has a corresponding bra. Every ket has a corresponding bra vector, unique bra vector, and vice versa. Now, there's a one-to-one correspondence, so for that one-to-one correspondence, that is, if we have A psi ket or ket psi, B ket phi, that corresponds to the complex conjugate, because A and B are complex numbers over here. So complex conjugate of A bra psi plus B star or B conjugate phi bra phi. Now the common notation that is for this we have got A psi in the ket bracket. As A comes outside of it, the ket bracket remains as such. We have, this is A psi. Now the other part where A is contained within the bra vector, if that is to be taken out, we take out the conjugate of it and we have the psi bra vector. Now in case of the scalar product, we must consider the ordering of the vectors that we have at hand, because phi psi, the inner product or the scalar product of that, the conjugate taken will give us psi over phi. So this property can clearly be explained by considering this equation that we have at hand, where we can take phi psi, the conjugate of it is going to give us, now remember phi psi over here was in that form, so we first of all use that form, that is the conjugate of phi and that's obviously RT, function of R and T, psi RT, and finally d cube R, and the whole conjugate of that is going to result in psi star, or the conjugate of it, RT phi RT d cube r, which is nothing but equal to this. So that's the case of ordering of the scalar product. Phi of psi won't be the same as psi and phi because it's the other one is the conjugate of it. Until and unless, of course, both psi and phi are real. Now, if they are real, then we would have had this case where this is a special case, of course, where psi over phi, the inner product on this side, is equal to the inner product with the change in the ordering. Now, for any state vector psi ket of the Hilbert space, the norm which is the inner product of psi with psi, that is real and positive. Okay, and if the state is normalized, of course, if the state is normalized, then we are obviously going to get the scalar product to be equal to 1. Now we discuss a term called Schwarz inequality, which states that for any two given vectors, that is psi and phi, which belong to the Hilbert space, they show the property where we have the modulus of the scalar product and the square of it will be less than the inner product of the individual vectors. Now, in case we have them to be linearly dependent, which means in case psi is proportional to phi, which means psi is equal to some scalar multiple of phi, then we have the relation to be an equality, right? Then the relation is an equality instead of the inequality. Now, the Schwarz inequality that we have just considered or just studied over here, that's quite analogous to that in the real Euclidean space, where we have the dot product of A with B, any two vectors given, and the modulus of it taken squared will be less than A square and B square, that is the dot product of A with itself and B with itself. That's analogy that we draw with the Euclidean space. Then we have the following qualities where we have the triangle inequality. You can always compare these things with the Euclidean space, and same with the case of orthogonal and orthonormal states. Orthogonal when we have the inner product of the given vectors to be equal to 0, that is they are the bases are normal to one another, they are orthogonal. And as for orthonormal, we have the orthogonal condition as well as the case of normalized vectors. So these are some of the formalisms that are associated with the Dirac notations. Having known about them, And how they are going to be used is we are just going to get a glimpse of it with a few numerical examples that we are going to discuss right now. So let's get started with that in the next page. Now what we are going to study over here, or we are going to know that the representation of the kets and the bras are in the form of matrices. As it is because of these formalisms that they are used as matrices is the reason why they are going to be so beneficial and useful to us in determining various behavior and various structures of quantum mechanics. So let's consider the first things that have been provided to us is that we consider a ket vector. So the ket vector has been provided, which is of the form psi. The ket vectors are always the column matrices, while the bra vectors are the corresponding row matrices taken the transpose of, and with the complex terms they are taken the conjugate of. So we have minus 3i, 2 plus I, 4. This is one column matrix, and the other one for phi, ket phi, that is equal to supposedly 2 minus I and 2 minus 3i. So these are the two vectors that have been provided to us. Now the first thing that we need to know is we wish to find the bra phi vector. Now for that, obviously, as I mentioned, that it is nothing but the row matrix, and in the row matrix we are going to have the transpose of it, and the complex term is going to be taken the conjugate of. So we have 2i and 2 plus 3i, that is from this one that we have learned. Now we wish to calculate the scalar product phi with psi. So in order to obtain that, we take the bra vector, that is 2i, 2 plus 3i that we have just obtained, and that is to be multiplied to the column matrix, that is 3 minus 3i, 2 plus I, and 4, because we have the ket psi. So that eventually gives us minus 6i plus 2i minus 1, and the 2i plus 2 plus 3i gets multiplied to 4 to give us 8 plus 12i. So that finally leaves us with how much is it? Well, it is 7 plus 8i. Now obviously the product cannot be taken in this form where we are taking supposedly we wish to calculate the ket with the ket, or we wish to calculate the bra phi with the bra psi. These do not really make sense, because these will be either column matrices multiplied to the column matrices and row multiplied to row matrices, which is not possible in the matrix multiplication. So it's not possible, and it makes it completely meaningless. Now, as far as the inner product, that is the scalar product that we have been discussing about, which is this one, as far as that is concerned, what we know that it must be analogous to the scalar product of the ordinary vectors in the Euclidean space, where the representation of any given two vectors, supposedly we have A dot product with B, gives the projection of B on A. Similarly, the product over here, that is phi, bra phi with ket psi, we have the representation. In that representation we have the projection of psi onto the phi space or phi vector. Now, in case of normalized states, the quantity that has been obtained, that is the inner product of phi with psi, that represents the probability amplitude that the system states psi will, after measurement, be performed on the system to be found on in another state phi. So basically what we are doing is we are taking the projection, and also we are considering we are obtaining the probability of finding the projection of one vector in the other vector with that dot product, which is analogous to that in the Euclidean space. Now let's get on with another example so that we get a detailed discussion or detailed view of the topic. Now we have supposedly we have the ket vector to be equal to 3i phi 1 minus 7i phi 2 ket, and we have the chi ket vector to be equal to minus phi 1. Phi 1 and phi 2 kets are obviously the basis over here, so 2i phi 2 ket, and we have both phi 1 and phi 2 kets to be orthonormal. Now from that we wish to calculate in the first place psi plus chi ket, and also the psi plus chi bra. So this is fairly easy. The first things first, we have psi plus chi ket term to be equal to, this is simply individually we are taking the sum of psi and chi, and that must be equal to both those terms. The phi 1 terms, we have 3i minus 1 of phi 1 ket, and secondly we have minus 7i plus 2i, so that leaves us with minus 5i phi 2 ket. And as for the second case, that is the psi plus chi bra vector, we have the bra psi, and that is added to the bra chi vector, and that leaves us with, well, now as for them, if we consider, now these are not given in the matrix column matrix form, so what we must also remember, the property which we considered over here, that is in the properties portion, that you can see the one-to-one correspondence where a psi plus b phi ket forms, they correspond to a conjugate psi bra, and that b conjugate that is added to the b conjugate bra phi. So we are going to use the same property over here, and that gives us the conjugate term of 3i minus 1, which is going to give us minus 3i minus 1, and that has phi 1 bra phi 1, and this is going to be plus 5i bra phi 2. Now after this we supposedly wish to calculate the scalar product of psi with chi, and also chi with psi. So if we wish to obtain the scalar product, now the first term over here, that is psi with chi, for that we have already obtained the bra psi vector, which is this one, and we will be using that. So we have minus 3i minus 1 bra phi 1, and that will be multiplied to, no, that's actually not the one, because I was getting confused a bit with all those notations. This is not the one that we are seeking. We are seeking the bra notation over here. So over there, if we are going to use that, I'm just striking this off, or rather I'll erase them for you. So for this we have minus 3i bra phi 1 plus, that's going to be plus because we are taking the conjugate over there, so plus 7i bra phi 2. Now that will be multiplied to, the ket chi. Now, just like the scalar product that we have learnt in the Euclidean space, and as for the normalized condition that we have over here, so from that the phi 1 and the phi 1, that is the bra phi 1 and the ket phi 1, the product of them is going to give us 1, while the product of the bra phi 1 with ket phi 2, or even with the bra phi 2 and ket phi 1, that is going to be 0, which means that we have phi 1 with phi 1 to be equal to 1, which is also the case with phi 2 with phi 2. But as for phi 1 with phi 2, that is going to be 0, which is also the case for phi 2 with phi 1. So using this, we can have the result pretty easily. That is the minus 3i term, which is the bra phi 1, that only gets multiplied to the product is obtained for the ket phi 1, and phi 1 terms, they go to 1 as they are normalized, and we are left with only plus 3i. So as for the first case, we can directly write it as plus 3i. With gradual regular practice, you can obtain it fairly easily. So I am writing it as like that, that is 3i, phi 1 and phi 1, they go to 1, and the minus multiplies with minus 3i, so that becomes plus. And as for phi 2, we have 7i multiplied to 2i, and that is going to give me minus of 14. So this is what we get for psi with chi, the inner product. Now as for the inner product of chi with psi, I leave it to you to try it, because you now know how to obtain this value. So I'll leave it to you. We'll try one more question related to this, or even we can continue if time permits. Now suppose we have the ket psi 1 to be equal to that, and ket psi 2 to be equal to that. Then where obviously these are the kets that we have for phi 1, phi 2, phi 3 and phi 4, they are orthonormal kets, and we have a as a constant term that is multiplied to the ket phi 3 over there at the top. Now we wish to obtain the value of a, so that we have psi 1 ket and psi 2 ket to be orthogonal. Now in order that we have them to be orthogonal, we must have the product, the inner product of psi 2 with psi 1 to be equal to 0. That's what we need. It is a must case. So in order that we get that, first we have to find the inner product. In order to obtain the inner product, what we get is That means this is the solution of that. So for psi 2, the bra form, there we have it to be equal to 3 bra phi 1 minus I, is it? No, that's going to be plus because we have the conjugate of it, the complex form, bra phi 2, and the third one having phi bra phi 3, and the last one being minus bra phi 4. And that will be completely multiplied to this term over here, that is for psi 1 we have 2I ket phi 1 minus, not minus but plus phi 2 ket phi 2 minus a phi 3, and finally we have plus 4 phi 4. So it's fairly easy because we know that phi 1s and phi 2s and phi 3s and phi 4s, the inner product of them is going to be 1. And the inner product of phi 1 and phi 2 in any ordering is going to be 0. So we have the first term as 6I plus I minus 5A minus 4, and that goes to 0. And with that going to 0, we have the value of A now to be equal to minus 7I minus 4 divided by minus 5. It's obviously going to be equal to 7 minus 7I plus 4, with them going to the other side, and minus 5 divided to that. Or we can just take the minus away from the denominator. So we have 7I minus 4 over 5, which is the value of required value of A, so that we have the orthogonal condition to be satisfied. So that's it about Dirac notations and the formalisms involved, and also a few mathematical examples to help us understand the concept of these notations, how they are used, and to what extent will they be used further in the upcoming topics. In the next video on this series, we'll be discussing about operators and many more things to come. So thank you for watching. Stay tuned.